You're given a palindrome string S and a number K, and asked to find the kth smallest rearrangement of its letters that still reads as a palindrome, when all such rearrangements are listed in alphabetical order. If the string can't be rearranged into that many distinct palindromes, you return an empty string instead. Beginner level. Hi. Don't worry if this problem sounds scary. We're going to slow down and go step by step. A palindrome is just a word or string that reads the same forwards and backwards, like above. Here's the big secret for today. Because a palindrome is symmetric, if you figure out the left half, the right half is just a mirror image of it. You don't have to think about it at all. That one idea makes this whole hard problem much easier. First, some vocabulary. A permutation just means rearranging letters into a different order, like turning AB into ba. Our job is to find one specific rearrangement, the kth one, if we listed all the valid ones from smallest to largest. Now here's the twist. If some letter appears an odd number of times, like 3 A's, you can't split it evenly into two equal mirrored halves. So one single letter has to sit by itself in the very middle. Keep that in mind, we'll use it soon. Let's make this concrete with a tiny example. Take the string Abba. If we shuffle its letters around but only keep results that are still palindromes, it turns out there are exactly two, Abba and Bab. Now line them up alphabetically, first Abba, then Bab. If someone asks for k equals 2, that just means give me the 2 and 1 on that list, which is Bab. That's the whole task. Find the kth one on this alphabetical list without writing out the whole list. Before we code, let's meet three simple ideas. And don't worry, I'll show you exactly how each one is used in a moment. First, a frequency jars, which is just a fancy way of saying we count how many times each letter shows up. Second, factorials, which is a math trick for counting how many ways you can arrange a group of things without actually listing every single one. Third, greedy picking, which just means we decide one letter at a time, going in order, like turning the dials on a combination lock one click at a time. When I first saw a problem like this, my instinct was just generate every possible rearrangement, then throw away the ones that aren't palindromes. That works for a tiny string like Abba. But if the string has thousands of letters, the number of rearrangements becomes so enormous that no computer could ever list them all. So here's our shortcut instead. Since we already know the answer must be symmetric, we only need to figure out the left half. The right half is automatically decided. It's just the left half written backwards. Let's write our first bit of code. First, we count how many times each letter appears in the string. That's what counters does for us. It's like counting coins into little piles. Remember that odd one out letter from before? We find it here, and it becomes the lonely middle character. Every other letter gets cut exactly in half, since half goes on the left side and the matching half goes on the right. So now we have a much smaller collection of letters to think about, just the left half. Here's the part that feels like magic the first time you see it. There's a math formula that tells you exactly how many different ways you can arrange a group of letters, just from counting them, without ever writing any of the arrangements out. We use that formula to instantly check. Does a kth arrangement even exist? If k is bigger than the total number of possible arrangements, we can just stop right away and return an empty string. No wasted work. This step decides our letters one position at a time, going in alphabetical order, always trying the smallest letter first. For each guess, we ask, if I place this letter here, how many valid endings could follow? If k is small enough to fit inside that count, we log that letter in and move to the next position. If not, we subtract that count from k, put the letter back, and try the next letter in line. Think of it like flipping through pages in line. Think of it like flipping through pages in a phone book, skipping past whole sections at once instead of checking one entry at a time. We already did the hard part. We built the left half letter by letter. Now finishing is easy. Stick the letters together into a string, add the lonely middle letter if there is one, and then tag the same half onto the end, but reversed. That's it. No more decisions to make. The mirror shape takes care of the rest automatically. Let's try a hand twist example together before I show you the answer. Say S is C bab C and K is 2. Pause the video and try to work it out using what we just learned. Remember, you only need to think about the left half. Let's walk through it together. The left half only has one B and one C to work with, so there are only two ways to arrange them, FC or CB. Alphabetically, BC comes first, so FCB is second. Since K is 2, we pick CB. Now mirror it around the middle letter, A, and we get CBBs exactly matching our original string. See, the whole answer came down to just ranking that tiny two-letter half. Just so you understand why our trick matters, let's talk about the obvious, simple way most people would try first. You could use a built-in tool to generate every single rearrangement of the string, keep only the ones that are palindromes, remove duplicates, sort them, and pick the kth one. It's very easy to write and easy to trust for a short string. The problem is, it completely falls apart once the string gets long, which is exactly what we'll see next. Let's see the difference in real numbers. With just 10 letters, the brute force method has to check over 3.5 million rearrangements. Our counting trick, using the same 10 letters, only needs a few hundred small checks, and the gap gets dramatically worse the longer the string gets. This is why, for anything beyond a tiny example, our smarter method is the one to use. Let's double check our solution handles the tricky situations. If k is bigger than the total number of possible arrangements, we already catch that early and return an empty string. If every letter in the string is the same, like aha, there's only ever one possible arrangement, so k has to be exactly 1, otherwise there's nothing to return. And since we're told the input is always a valid palindrome to start with, we never have to worry about more than one odd count letter. That headache is already avoided for us. Let's recap what we learned today. Remember that half the problem idea from the very beginning? That was the whole solution. Split the string into a left half plus one possible middle letter. Use factorials to count arrangements instead of listing them. Pick each letter of the half one at a time and then mirror it to get the full answer. If this clicked for you, that's great progress. This pattern shows up in lots of other problems too. New video tomorrow. See you then.